In this video, we want to take a look at examples number 3 and 4 out of the notes to try to understand how we can better use Green's theorem in other variety of situations. So take a look here at example 3. I want to evaluate, again, this particular work integral, where C, the curve that has, again, a positive orientation indicated by this circle, is a circle of radius 2 centered at 1, 5. All right. Well, one thing that I might notice immediately is that if I have a circle of radius 2, and it's already indicated here that it has positive orientation, I can make the following notes immediately. So I'll say, we immediately note that C is a smooth, simple, closed curve with positive orientation. Right? So I already have that. That's fantastic. Now I can go ahead and start to think about, okay, so let's see. My P of xy here is going to be, again, the thing that's going to be in front of my dx, and my Q of xy is going to be the part that's in front of my dy. So I have these two functions here. And I want to also understand if these have continuous first derivatives. But I think that definitely this guy over here is just a polynomial. This is a polynomial plus like some exponential functions. So I should be able to say that these guys here have continuous first partials definitely on the region enclosed by C. Again, remember that we call that region D. Okay, so I could then go ahead and start to set up Green's theorem right away. So by Green's theorem, my integral here is going to be equal to a double integral over that region D. And I just have to remember that I'm going to be using here my partial of Q with respect to X minus my partial of P with respect to Y. All right, so let's take a look here. Q. I want the partial derivative of this with respect to X. Oh, well, that's pretty easy. That's just 2. And then I want to subtract the partial derivative with respect to Y. And, oh, that's going to be 3. And I just have to integrate this. So if I look, this is actually just -1 times the following. Ooh, and actually, this is really great too, because remember that what I have right here is an integral with a 1, a double integral with the 1. Do you remember what that happens to measure? Well, you might recall that this here is actually just going to be the area of D. But if D is a area of a circle, right? Because I had C was a circle, so D is the area inside of it, and it was a circle with radius 2. What's the area for a circle of radius 2? Well, that should be pretty easy to see, that that's just going to be 4 pi. So my answer here is just -4 pi. In this case, since I got down to a simple area, I didn't even have to define the region D, and I didn't have to do a double integral. This is really, really nice, because I had a nice, easy geometric shape. Now, this may not always happen, but it's nice and easy to try to go ahead and be able to implement this when the appropriate situation arises. Now, of course, if I didn't catch this, I still could have gone ahead and defined D, but maybe I would have defined it in polar coordinates, since it would have been a circle. Let's take a look now here at example number 4. Let's suppose that C is a positively oriented, piecewise smooth, simple closed curve in the plane, and that D is the region that is bounded by C. Okay. True or false? This integral here yields the area of D. Well, here's what I'd like you to do. I'd like you to try to pause the video and attempt this question on your own. And I'd like you to try to see if you can use Green's theorem to help you confirm whether this is true or false. Pause the video, give it a shot, and then unpause to see me work through the answer. Okay, so the answer that I got is that this is definitely going to be true. Now here's how I can see why. I can easily see that Green's theorem here definitely applies. I'm not going to write out all the detail, but I can see that C already meets all the conditions. And if my P is this negative y over here, keep in mind, it's the thing in front of the dx. My Q is x. That both has, those both have continuous first-order partials on the region of D, because they definitely are going to have continuous first partials on all of R2. But by Green's theorem, I can easily state that this integral that I'm working with here, is going to be equal to a double integral over D, still has the 1/2 in front, and when I do my partial with respect to y, my partial with respect to x is going to be 1. My partial with respect to y over here is going to be -1. And so I should rewrite that a little more carefully. It's going to be minus -1. Then what I'm going to be left with here is really 1/2 times the double integral over D of 2 dA. But of course that just turns into the double integral over D of 1 dA. And like we had kind of seen above, this actually does represent the area of D. So this is indeed a true statement.